Good. So I would like to start by thanking Professor Czizik for invitation to speak at this interesting conference. And I'm going to speak about paramagnetic relaxation in solution, and it will be an overview of the field. So I'm going to start by telling you what paramagnetic systems are. Then I'm going to give you a kind of historical picture. We start with early days of paramagnetic relaxation. We are going to discuss what is wrong with early theories, and then we are going to talk a little bit more about the complications, and towards the end I will also give you some experimental examples and examples of applications. So paramagnetic molecules contained I'm sorry contain unpaired electrons, and an unpaired electron spin gives rise to a very large magnetic moment, which is about 650 times larger than that of proton. Paramagnetic molecules are often studied by SAR, but they also have a very strong influence on solution NMR properties, such as relaxation, shifts, splitting. I will concentrate in this talk on relaxation. There are many types of paramagnetic molecules, but I will concentrate on the three types shown here. So I will mention organic radicals, transition metal ions and complexes, and oxygen gas. Now, I want to begin with, as Professor Fresard did, with very old history of NMR, and mention the relaxation classic, the Bloomberg and Purcell-Pound paper from 1948, which contained this picture that I have here. It's the relaxation rate of water protons as a function of concentration of some paramagnetic ions. So the history of paramagnetic relaxation, we can say, is as long as the history of NMR relaxation in general. Now, some general things about paramagnetic relaxation. When you have paramagnetic species in your solution, they enhance relaxation of nuclear spins. And this happens independently of chemical relation. We can talk about three cases. We can have the nuclear spin residing in the same molecule as a paramagnetic center on a long time scale, and this might be the case, for example, for metalloproteins. We can have a situation where nuclear spins are in ligands which exchange rapidly. For example, metal ions in water, the water molecules exchange rapidly. And then we can have a situation where we have a nuclear spin in a different molecule than the electron spin, and we have only relatively weak intermolecular interactions. And this might be the case if we look at nitroxide in organic solvents. Now, early days, we can say, I showed you already the very early days, but what I mean by early days is something from the middle of 1950s. So Solomon in 1955 presented a theory of dipolar relaxation, which corrects some mistakes, smaller mistakes of the BPP paper. Then a year later, Solomon and Bloombergen found that also the scalar interaction, not only the dipolar interaction between the unpaired electron spin and the nuclear spin should be included, but also the scalar interaction. And these works apply for both diamagnetic and paramagnetic systems, assuming that nuclear and electron spins are in the same molecule. Now, one thing that you have to consider, which was also realized very early on in the early 60s, is that the situation with chemical exchange, so such as aqueous solution of transition metal ions, we need to understand the relation between what we measure, the relaxation rates or shifts that we measure, and what we formulate theoretically. It is namely so that the chemical exchange effects influence the measured properties in a non-trivial way. It's rather simple for T1, where the measured T1 in the paramagnetic system is given by this expression, where we have the molar ratio of the bound and free solvent, and we have here in the denominator we have the sum of the relaxation time in complex and the exchange lifetime. So the exchange lifetime actually influences what we measure in a not completely trivial way. Then we have similar relations for T2 and for the shift, which are a little more complicated. Now, as I said, what makes paramagnetic systems special is that we have this huge magnetic moment of the unpaired electron spin. And this huge magnetic moment has one more interesting property. It has a very rapid relaxation. So the magnetization due to electron spin is relaxing rapidly to equilibrium. Already in the early 60s, in 1961, Bloombergen and Morgan formulated the theory of electron spin relaxation for aqueous transition metal ions with spin 1, electron spin 1 or higher. And they obtained this simple equations for T1 and T2 of the unpaired electron spin, which were valid for oscillating, or we can also call it transient, zero field splitting being present. Spin 1 or higher means that we have the zero field splitting interaction present, and the magnitude of this interaction influences very much the relaxation times of the electron spin. This theory was also valid for the case of short correlation time, so rapid motions. So if we want to summarize the early days, we can state that we can formulate a complete theory if we combine the Solomon-Bloombergen and Bloombergen-Morgan theories, and we obtain what is called sometimes SBM theory, Solomon-Bloombergen-Morgan theory. This allows us, according to this theory, we can write what is known as modified Solomon-Bloombergen equations, which were formulated in the late 60s, early 70s. So we have the dipolar and scalar terms. We have correlation times, which include the electron relaxation, exchange, and the reorientation. Now, what is wrong with the early theories? Why do we need anything better? Well, there are several reasons. One is that the SBM theory is valid in the high field limit. It assumes that the dominant interaction in the system is the Zeeman interaction, the interaction between the spin and the external magnetic field. It may be a problem because we often want to measure at low magnetic fields in field cycling experiments that I will come back to. Another problem is the so-called decomposition approximation, which means that you assume that electron spin relaxation is uncorrelated with rotation. And this is, as I said, we assume that we have only transient zero field splitting interaction when deriving the Bloomberg and Morgan theory. And this may not be the case in many, many cases. the composition approximation is strictly applicable only for highly symmetric systems. Then we have the third problem, which is the validity of the perturbation regime, which is also known as Redfield limit. The problem there is that interactions which involve electron spin are very strong compared to nuclear spins. So it's not sure that if we take a product of the interaction strength squared with the correlation time squared, we get something much less than 1. And if this is not fulfilled, then we are out of Redfield limit, we are in trouble. So what can be done about it? Again, in the 60s, 70s, and 80s, some people did important developments. What was developed then was the low field theories, which were valid for the case of low field. So it solves the problem with the Zeeman limit. And also it allows to include some angular relations between the dipole-dipole interaction and the zero field splitting interaction, provided now that the motion is slow, that the rotation is slow, that the rotation does not directly influence the relaxation, but only provides some averaging of interactions over the rotational motion. Now, one variety of this, which was developed in the late 90s, is known in the literature as modified Florence approach, and it uses a Redfield limit description of the electron spin relaxation, but it uses also the low field approach as formulated by Linda and other people and people in Florence that I mentioned earlier on. So we can then do the calculations just to see what happens, assuming an angle to compare the Solomon, Bloomberg, and Morgan, which is the top curve here, with what we get, assuming a certain angle between the dipole-dipole interaction, which is the main interaction between the electron spin and nuclear spin, and the zero field splitting interaction. Zero field splitting interaction is similar formally to the quadrupolar interaction, but it's an interaction of the electron spin itself. Now, what happens if we are in the situation where this perturbation limit is not valid? So we are out of the Redfield limit. This is described, among other, by the theory which we call the slow motion theory. Sometimes it's called the Swedish slow motion theory because it was developed by some Swedish groups in the 80s. So what we basically do is that we formulate a theory which is valid outside of Redfield limit. So we have to replace the Redfield equation for the nuclear spin relaxation by what is called the stochastic Liouville equation. It's a more complicated way, but more general way. And in order to do that, we introduce what is called a composite lattice, which is a lattice containing the classical motions such as rotation and distortion, which are also in the classical part of the Redfield theory. But then we also include some interactions such as electron Zeeman and the zero field splitting, which are the quantum mechanical interactions. We include even them in this composite lattice. And there is still the coupling between the nuclear spins and the composite lattice through the hyperfine interaction. And we can derive the relaxation rate for nuclear spins. And this depends is given by a spectral density function, which is calculated numerically by inversion of a very large matrix in the Liouville space. As I said, this was developed by the Swedish groups in the 80s and the 90s. Now, there is a very different way, conceptually very different way to move to this. And one of the first people to do this was Odelius, which was at that time my student. We call this approach the spin dynamics. So in this approach, we use quantum chemistry to calculate zero field splitting along some time of trajectory, which gives us the time variation of the zero field splitting. And if we have a time variation of the zero field splitting, we can calculate the time correlation functions for the variation of the spin Hamiltonian. And from there, we can calculate the electron nuclear spin relaxation. And here are some data. This is the time correlation function for the electrons, for the zero field splitting in aqueous nickel obtained in this way. And this is the field dependence of the electron spin relaxation based on this data. So we can do a lot of nice things, which are, however, computationally very demanding. So the idea of spin dynamics is very attractive in many ways because it allows you to describe the physics of your problem in a nice way, and you can use well-formulated approximations. So people such as Sharp, Rust, Fries, around 2000, they proposed a simpler spin dynamics approach when you assume a constant amplitude of static zero field splitting, which is modulated by rotation, and the transient zero field splitting, which is modulated by distortion. So you assume that both these interactions have a given strength, and then their orientation changes with time by diffusional motion. So this allows again to calculate time variation of the spin Hamiltonian, electron spin relaxation, and nuclear spin relaxation. And all these calculations are done in time domain. All the calculations in the slow motion approach are calculated in frequency domain. So the mathematics is very, very different. But still, we thought the people doing the spin dynamics and we doing the slow motion theory, we decided to join our forces and calculate the PRE against the magnetic field for a large number of different parameter sets using their model and our model. And lo and behold, the model developed in Grenoble by Bellerinsky and Fries, and our calculations, the Stockholm model, they were exactly on the top of each other for all 50 different parameter sets. The third model, which was included in the comparison, was a little bit different, and we understand why it is so. His Sharp's treatment of the electron spin relaxation is a little bit different. So this gives us a nice theory, but there are still complications. Curie spin relaxation is one such complication. And this is an interesting field, but for saving time, I will not talk about it. I will just tell you that there is a theory of this phenomenon formulated in the 70s, but now it seems that there is a new theoretical framework published last year, which will allow a more consistent description of this phenomenon. The second complication is the intermolecular relaxation. As I said, we can have the paramagnetic relaxation enhancement also in a situation where the paramagnetic species and the nuclear spins are in different molecules and move more or less freely with respect to each other. Intermolecular relaxation is understood since many years. We have also formulated the slow motion formulation of this type of relaxation processes, and it works, but it's very time consuming. Now, let me turn to experimental situations. What can we do in terms of experimental studies of paramagnetic relaxation enhancement? Well, one obvious variable to change is to change temperature. And we can thus plot the relaxation rate, in this case T2, as for oxygen 17, as a function of plotted against reciprocal temperature, and these are data taken from Hugi and co-workers in Lausanne, published 87. This type of measurement allows to clarify the relaxation mechanism, the reaction mechanisms. Here we have a situation of titanium salt in water, and we can study the mechanism of water molecule exchange between the bound side and the free side. Sometimes this can also be combined with variable pressure and allows then even more detailed information of concerning the reaction mechanism. Now, another experimental variable is the magnetic field, and this is very powerful way of studying the relaxation processes. This gives you information about the physics of relaxation. And there is a very nice experimental technique which allows you to do this, which is called the fast field cycling, developed by Redfield, the same Redfield who did the theory, Koenig, Nowak, also a long time ago. So basically the method means that you magnetize your sample in a magnetic field, then you quickly switch the field, change the magnetic field to the field at which you want to measure relaxation. You let the system relax for some time, and then you detect. And this type of measurement is known as nuclear magnetic relaxation dispersion, and they provide a critical test of relaxation theory. So these are very, very important. And also, there are many important applications of this type of measurements. One is characterization of the contrast agents for magnetic resonance imaging. Contrast agents for MRI are often paramagnetic species, often gadolinium complexes. Now, nowadays in NMR, many people are interested in proteins, and this type of approach with paramagnetic relaxation enhancement works also for proteins. And there are basically two types of measurements. You either measure on metalloproteins, which contain a paramagnetic metal, or you can bind a paramagnetic tag to your protein and put your paramagnetic metal in this tag. These measurements are typically done at high field and high resolution, and a lot of measurement of this type was reported by and developed by Bettini and co-workers in Florence. Now, the complication is that the rapid relaxation makes the signals from nuclear spins near the paramagnetic center invisible. This can be resolved by measuring not on protons, which are particularly strongly affected by paramagnetism, but like carbon-13 or nitrogen-15. There is also another property that you can measure in this kind of systems, and this is to measure pseudo-contact shifts. And usually, the pseudo-contact shifts are in fact a better source of information. Now, more recently, Clore at NIH proposed that one also could use this type of measurements to study sparsely populated transient excited states in proteins, conformational changes and things like this. Now, let me show you an example of this type of measurement. Here it is. The data are NMRD, so nuclear magnetic relaxation dispersion, for a contrast agent of a gadolinium salt in water, and we measure water proton relaxation. And you can see that there is some structure in this data, this data can then be fitted using different theories, more or less successfully. The data I show you were fitted based on the slow motion approach, and I think it's pretty good. Now, gadolinium has an interesting structure at rather low magnetic fields of the gadolinium solutions. Some ions want higher fields in order to get any action. If you just measure at low field for nickel in water, you get a flat line. Interesting things start about half Tesla and continue until about more than 30 Tesla. And these are measurements from my group done together with many collaborators at High Field Lab in Grenoble, when you can measure proton T1 at up to 32 Tesla. Fitting was based on the inner sphere relaxation and slow motion theory. The fitted data are, let me see, I don't see the end of the picture. We also tried to do the fitting, including the inner and outer sphere relaxation, but this turned out not to work very well. Now, a new tool, experimental tool, which was developed rather early. The first attempt to do this was reported by the Lausanne group in 1996, is to use a combination of ESR and NMRD, and actually to formulate a theoretical model and to fit a theoretical model which would present both which would be able to interpret both the NMRD and the ESR data. And we did that using slow motion theory also. And this is something that I think is likely to be much more useful in the future. So I mentioned to you that when I talked about slow motion theory, that there is a big matrix in the Liouville space, which we formulate, which can have dimension of hundreds of thousands linear dimension. Now, when we look at these 3 elements, these 9 elements in the inverse, this little 3x3 matrix, in the inverse of the big matrix, we get information about NMRD. When we look at this little corner here in the matrix, we get information about ESR. So it's very easy to give a consistent description of both these kinds of spectra. And we have done that. We used first, we used a contrast agent, again, gadolinium compound. We fitted the data using NMRD. We are more familiar with doing that. And then we simulated ESR at high field. And here the the black line is experimental data, and the red lines are calculated, simulated data. So the solid red is for isotropic G tensor, and dashed is for anisotropic G tensor. And it turns out that we were forced to invoke the anisotropic G tensor in order to reproduce the line shape. But according to the ESR people, this is reasonable to expect. We need a low anisotropy of the G tensor. Okay, I think I skipped this one, and I come to conclusions. The conclusion is that the theory of paramagnetic relaxation is quite complicated. And this is mainly because of the interactions involving electron spin and their high strength. In some limiting cases, it is possible to describe these problems by simpler theoretical models, but in general, we need a rather complicated theoretical apparatus using either slow motion theory or spin dynamics in order to predict the relaxation rate and its field dependence. I believe that the variable field spin lattice relaxation measurements are very informative indeed. And I know that by now this type of experimentation is quite common. A combination of ESR and MRD, I think, will probably be used much more in future. And the paramagnetic protein work remains a very hot field. So I would like to finish by acknowledging important long-term cooperation with Danuta Kruk and also long-term collaboration with people in Florence, Bettini, Lukinat, and Parigi, and long-term financial support by the Swedish Research Council. And with this, I want to thank you for your attention.
Okay, so thank you very much, Professor Kowalewski, for your kind accuracy. It's just in time schedule. Nice. So maybe I would like to ask one question only, okay?
Yes, sure.
My question is next. Mostly all theoretical models which you have considered today deal with nuclear spins equal 1/2. But what will happen if we have the quadruple effect? I mean, the spin is will be, let's say, more than 1/2.
Well, if you look at protons, for example, in paramagnetic systems.
Yeah, 1/2.
Yes, you practically don't need to worry about the different relaxation mechanism because the paramagnetic mechanism is dominant. Yeah. If you have a look at quadrupolar spins, they are also influenced by the paramagnetic species. But you have also the efficient quadrupolar relaxation, so you have to be careful to discern.
For instance, deuterium, right?
Yes.
Deuterium, heavy water.
Well, actually, if we go back a few slides, I had this one here. These data are for oxygen 17, which is a quadrupolar spin.
Yes, because oxygen 16 have that magnetic moment.
No, exactly.
Yeah.
So the same approach can be used for quadrupolar spins. The difference is that, as I said, that you have to separate the paramagnetic relaxation and the quadrupolar relaxation, which may be non-trivial.
Yeah, not trivial. Okay, so thank you very much indeed. Is there any other question?
May I ask?
Yes, of course.
Yes. Joseph, what is your opinion about the real significance of the spin-Curie mechanism of relaxation?
Well, it is important in situations. Let me see.
Slow motion.
Yes, if you have big molecules such as proteins, if you have slow rotation, the slow rotation will make the Curie spin relaxation efficient. So we have big molecules, viscous solutions, then you get a large broadening caused by Curie relaxation. For T1, probably Curie relaxation is not very important.
But what about the experimental confirmation of this mechanism?
I can't give you any special references, but there are data on this, so you can find it in the literature.
Thank you.
Okay. Is it